Greetings, stargazers, and welcome to this episode of Star Trails. My name is Drew, and I'll be your guide to the cosmos for the week starting August 11th to the 17th. There's a lot going on in the night sky this week, from meteor showers to planetary conjunctions. Later in the episode, we'll take a broad look at the world of radio astronomy and the amazing instruments that allow us to listen to the cosmos. So grab your binoculars or your telescope, find a comfortable spot under the night sky, and let's get started. The Perseid Meteor Shower peaks tonight and into the early morning hours of August the 12th. Known for its bright meteors and high frequency, the Perseids are a favorite among both amateur and seasoned astronomers. This year we're in for a treat, as the Perseids are expected to put on quite a show with little interference from moonlight. The Perseids originate from the debris left behind by the comet Swift-Tuttle. As Earth moves through this debris field, tiny particles collide with our atmosphere at incredible speeds, creating the bright streaks of light we call meteors or shooting stars. The radiant is the point from which the meteors appear to originate, and it's located in the constellation Perseus, which will be rising in the northeastern sky after sunset. For the best observations, find a dark spot away from city lights. The darker your location, the better your viewing experience will be. Once you've found your spot, lie back and look up, allowing about 20 to 30 minutes for your eyes to adjust to the darkness. The best time to view the Perseids is after midnight, when the sky is darkest and the radiant is higher in the sky. If conditions are right, you could see up to 100 meteors per hour. And remember, while the meteors will appear to radiate from Perseus, they'll streak across various parts of the sky, so keep your eyes peeled in all directions. The Perseids are known for their fast and bright meteors, which often leave persistent trails that last for several seconds. These trails can be colorful, sometimes appearing as red, yellow, or green due to the ionization of different elements in the atmosphere. And every once in a while, we get to see a fireball, an exceptionally bright meteor that lights up the sky. Comet Swift-Tuttle orbits the Sun every 133 years and last passed through the inner solar system in 1992. It's fascinating to think that each of those shooting stars is a tiny piece of this distant traveler, burning up in Earth's atmosphere after millions of years in space. The Moon will be in its first quarter phase on August the 12th. During this phase, it's half illuminated and visible in the afternoon and evening sky, setting around midnight. The Moon will wax towards a nearly full moon by the week's end. Mars and Jupiter will be in conjunction on August the 14th. They've been inching closer together in Taurus for the past few weeks, and now they're at their closest conjunction until the year 2033. For the best viewing, look eastward just before sunrise. Midweek, Saturn reaches opposition, meaning it will be directly opposite the Sun from Earth's perspective. Saturn will be visible all night, rising in the east at sunset and setting in the west at sunrise. The core of the Milky Way will be prominently visible in the southern sky this week. From a location with little to no light pollution, the Milky Way will appear as a bright band of stars stretching across the sky. Today we're exploring a truly unique way of experiencing the universe, not through our eyes, but through our ears. This is the realm of radio telescopes, the giant dishes that listen to the whispers of space. And we're going to hear some sounds in this episode that were all recorded with radio telescopes. Unlike their optical counterparts, radio telescopes don't capture visible light. Instead, they detect radio waves emitted by celestial objects. These waves are part of the electromagnetic spectrum, just like visible light, but they have much longer wavelengths. Picture waves in the ocean. They have peaks and troughs. The distance between one peak and the next is the wavelength. In the case of light and radio waves, this wavelength determines how we perceive them. Visible light has very short wavelengths, typically measured in nanometers, while radio waves have much longer wavelengths ranging from millimeters to kilometers. They pass through cosmic dust and gas clouds that often hide the secrets of galaxies and star-forming regions from traditional telescopes. No doubt you've seen a radio telescope before. Imagine a giant dish, often towering several stories high, silently tilting and turning as it scans the sky. This is a parabolic antenna that captures incoming radio waves and reflects them to a focal point, where a receiver detects and converts them into electrical signals. These signals are then analyzed to map galaxies, track cosmic phenomena, and even search for signs of alien life. A single radio telescope can weigh thousands of tons and may require precise alignment to function correctly. Arrays of these telescopes, like the Very Large Array in New Mexico or the Atacama Large Millimeter Submillimeter Array in Chile, can work together as interferometers, combining their signals to achieve resolutions far greater than any single telescope could alone. This technique is known as very long baseline interferometry and is crucial for observing distant cosmic events with high precision. The history of radio astronomy dates back to 1932 when Karl Jansky, a radio engineer at Bell Telephone Laboratories, identified radio waves emanating from the center of the Milky Way. This accidental discovery, sparked by his efforts to identify sources of static for transatlantic radio communications, marked the beginning of radio astronomy and opened up a new window into the cosmos. Then there was the work of Grote Reber, an amateur radio operator who constructed the first purpose-built radio telescope in his backyard in 1937. His pioneering efforts led to the first radio frequency sky map, revealing the universe in a completely new light. Fast forward to 1964, when Arno Penzias and Robert Wilson stumbled upon a mysterious faint noise that seemed to emanate from every direction. This noise turned out to be the cosmic microwave background radiation, or CMB, also known as the afterglow of the Big Bang, providing compelling evidence of our universe's explosive beginnings. The discovery of the CMB was pivotal in confirming the Big Bang theory, illustrating how radio astronomy can uncover the universe's most profound truths. It even earned them the Nobel Prize in Physics in 1978, solidifying the importance of radio astronomy in cosmology. For a deeper dive into the cosmic microwave background, go back and listen to episode 20. In 1967, the discovery of pulsars by Jocelyn Bell Burnell and Anthony Hewish introduced us to the lighthouses of the cosmos. These spinning neutron stars emit beams of radio waves with clock-like precision, offering a natural laboratory for testing the laws of physics under extreme conditions. Pulsars also serve as cosmic clocks, so precise that they've been used to test aspects of Einstein's theory of general relativity and to help detect gravitational waves from distant mergers of massive objects like black holes and neutron stars. The applications of radio astronomy continue to expand. Radio telescopes have mapped the cosmic web of dark matter, revealing the large-scale structure of the universe and giving us clues about the mysterious force driving its accelerated expansion. They have also detected mysterious fast radio bursts, FRBs, from distant galaxies. The origins of these brief yet intense emissions remain one of astronomy's enigmas. One of the most ambitious projects involving radio telescopes was the Event Horizon Telescope, which in 2019 produced the first ever image of a black hole's shadow, located in the galaxy M87. This landmark achievement demonstrated the incredible potential of radio astronomy in probing the most extreme environments in the universe. The black hole image was the result of a global network of radio telescopes working in unison to effectively create an Earth-sized virtual telescope. I'd also like to take a moment to appreciate the legacy of the Arecibo Observatory, one of the most iconic radio telescopes. Located in Puerto Rico and built in a natural sinkhole in 1963, the 1,000-foot-wide Arecibo dish was not only a marvel of engineering, but also a powerhouse of astronomical discoveries until its unfortunate collapse in 2020. Arecibo played a key role in several groundbreaking discoveries. In 1974, it was used to send the Arecibo message, a binary-coded message aimed at a distant star cluster serving as an early attempt at interstellar communication. That same year, Arecibo also confirmed the existence of binary pulsars, a discovery that provided the first indirect evidence for gravitational waves and earned the 1993 Nobel Prize in Physics. Arecibo's powerful radar capabilities enabled it to map asteroids, study planetary surfaces, and even search for potentially hazardous near-Earth objects, contributing to our understanding of solar system dynamics and planetary defense. Arecibo's loss was a significant blow to the scientific community, but its legacy lives on through the countless insights it provided into the workings of our universe. Its data continues to be analyzed, offering new revelations and reminding us of its pivotal role in the history of astronomy. I feel fortunate that I was able to see Arecibo in person back in 2009. It was truly a childhood dream of mine after seeing it in astronomy books and in movies like Contact and GoldenEye. Visiting Arecibo inspired me to get involved in amateur radio a few years later. Radio telescopes are also vital in our search for life beyond Earth. Projects like the Search for Extraterrestrial Intelligence, or SETI, use them to scan for signals that might indicate the presence of advanced civilizations in distant star systems. Each scan of the sky could bring us closer to answering the age-old question, are we alone in the universe? For amateurs interested in radio astronomy, there are opportunities to get involved. The Radio Jove project offers kits and resources to help you build your own radio telescope, allowing you to explore the universe's radio frequencies from your backyard. Observing phenomena like solar flares or even Jupiter's radio emissions can be a rewarding experience. The Society of Amateur Radio Astronomers is another excellent resource providing guidance, community, and inspiration for those eager to explore the universe through radio waves. I'll include a link to both in the show notes. Remember that every time you gaze up at the night sky, there's an invisible universe of radio waves. Thanks to radio telescopes, we can tune into this cosmic symphony and listen to the echoes of creation and the whispers of stars. That's it for today's episode of Star Trails. Before you go, I invite you to check out our weekly email newsletter on Substack, where you can receive night sky reports and astronomy news that we don't always mention on the podcast. We're also on Mastodon at *_trails, and we'd love to hear from you. You can find links to both services in the show notes. Also, remember our website, startrails.show, where you can find all of our episodes, including transcripts. Until next time, keep looking up and exploring the night sky. Clear skies, everyone.